Energy audits and retrofits are a huge part of the global construction market today, and one area where that's especially prevalent is in lab spaces. Typically, labs such as this one have been designed by rules of thumb and may have very active mechanical ventilation systems, but frequently the diffuser layout, placement, flows, and throws are not optimized because the labs were designed without the assistance of a computational fluid dynamics tool in order to fully understand the airflow. In the case of a retrofit, firms such as Blue Ridge Numerics, CFdesign will come in and model the actual space in a 3D CAD or BIM tool such as Autodesk Inventor or Revit or SolidWorks, and then measure the flows coming out of each of the diffusers and model the diffuser types in order to characterize the airflow patterns, air speeds, velocities, temperatures in a program such as CFdesign. Here we see the CAD connection between Inventor and CFdesign. And once the model is pulled in, we set up boundary conditions. So what are the actual flow rates, and what are the temperatures coming from the diffusers? What are the solar gains on the windows? Are there radiant panels? And are there heat loads generated by equipment inside, such as cryogenic freezers? After the boundary conditions, we'll set up materials and then mesh sizes to break the model down and solve it. And then once the simulation is run, we can see the airflow patterns from the diffusers. So here we see ceiling mounted side throw linear slot diffusers, which have over the years been adjusted by the maintenance staff in response typically to complaints from the occupants. So we see some very fast moving air indicated by the red regions, and in some cases the air is actually impinging on a jet from another diffuser. Now we'll switch that 2D slice showing that airspeed or velocity to be oriented horizontally, and there are always some pretty interesting flow interactions near the ceiling, and we also want to see what's going on in the occupied zone. What do those interactions cause? Another way to view this in 3D is with isosurfaces. An isosurface shows a cloud of air at one single velocity. So here's where the air is moving faster, close to the diffusers, and now as we drag this down, we can see where the air is moving slower and where those impingement or interaction effects may occur between diffusers. So in essence, where are the drafty regions in this model, and where are the regions where the air is very stagnant? Also, where is it hot and where is it cold? We can also look at local mean age of air. Frequently in these labs, safety concerns are paramount, so we want to understand, are there areas where if there is a spill or chemical contaminants, where would they accumulate? Even more important than the energy savings. So here we're showing the local mean age of air. And then finally, let's understand the thermal comfort or the actual temperature distributions in the lab. So again, using this 2D slice, we can see red indicates warm areas, green or blue indicates cool areas. So there are certain aisles that are very warm, there are certain aisles that are very cold. So this leads to, again, occupant complaints, tweaking of the diffusers, and really never achieving an optimized solution. So when going for these retrofits, what typically happens is we can help recommend different diffuser types, different diffuser placements in order to get this nice laminar, uniform, fairly unidirectional flow from the diffusers through the lab and out to the returns. Lastly, we'll show what we call traces or streamlines or path lines. Again, now it's as if you've injected imaginary dust or particles into the diffuser on the supply side, and now we can track these through the room. So another good way to monitor contaminants, thermal profiles, and airflow.